First of all, I'd like to thank the organizers for inviting me to give a talk to this very nice conference. Today, I want to tell you about some applications of computability to the study of finitely generated groups. And maybe this is more about having one paradigm of constructive mathematics than about actually computing things. But we'll see about that. So I will start by a motivating example for the study of computability in group theory. And the motivating example is based around cardinality. Suppose we have the following 5 group properties: hyperbolic groups, nilpotent groups, solvable groups, residually finite groups, and simple groups. And these properties have different cardinalities when we consider them applied to finitely generated groups. Hyperbolic and nilpotent, on the one hand, define countable sets, whereas solvable, residually finite, and simple groups define uncountable sets of finitely generated groups. This is obviously a very big difference. Now, suppose we restrict our attention to finitely presented groups. We get the following picture, which where the distinction that we had previously completely disappears. We now have only countable sets of groups, and we've lost one of the tools that we had to distinguish between hyperbolic, nilpotent, and solvable, residually finite, and simple. Now we introduce computability in the mix. We say that a set is recursively enumerable if there is a computable surjection from the natural numbers onto this set. This is really similar to being countable. We just ask that the surjection be computable. Once we have fixed this definition, we get the following picture. Hyperbolic and nilpotent groups define recursively enumerable sets of finitely presented groups. On the contrary, residually finite, finitely presented groups, this is not a recursively enumerable set. And for solvable and simple, whether or not they are recursively enumerable, this is an open problem. Here I've written down what the conjecture is. The question about simple groups has attracted a lot of attention lately because it's related to the famous Bone-Higman conjecture. But now you see what we've done. We had a distinction that we were able to make between hyperbolic, nilpotent, and solvable, residually finite, and simple. We were able to consider the cardinality when interested in finitely generated groups, and we lost the tool that is cardinality when studying finitely presented groups. But if we use computability theory, then we recover our tool to distinguish between those properties. And obviously the fact that, for instance, the set of residually finite groups is not recursively enumerable, this is relevant. It means that the question, what is a finite presentation of a residually finite group, this question doesn't have a very good answer. All right, so now I can tell you about the purpose of this talk. We want to do the same operation as above, but with the classification of group properties into open and closed in the space of marked groups. We want to be able to get a finer classification, classifying properties into computably open and computably closed in the space of marked groups, and hopefully this will teach us something. So to follow this, to do this, we first have to introduce the space of marked groups, and I'll tell you about these open and closed properties. Let me begin. A marked group is a finitely generated group together with a finite generating tuple. A morphism between marked groups is just a morphism of group, but that maps the first generating tuple to the second generating tuple, and while respecting the order of these tuples. So this is a morphism in the category of marked groups. Notice that there is at most one morphism from a marked group to another one, because the image of a generating tuple determines uniquely the group homomorphism. And two marked groups are isomorphic as marked groups as soon as there are morphisms in both directions. So this shows that isomorphism classes of marked groups are actually ordered by morphism, and they form a partially ordered set, which is a lattice in the order theoretic sense, which means that there are meet and join operations. All right. Another point of view on marked groups is very useful to introduce the topology that we consider on them. So we start by fixing a basis of a free group, and then we remark that a marking of a group is the same thing as fixing an epimorphism from the free group onto this group. Because obviously, if you have such an epimorphism, the image of the basis of the free group will give you a generating tuple for your group, and so it will give you a marked group according to our previous definition. And conversely, whenever you have a generating tuple, it will induce an epimorphism from the free group onto your group. And so these are just two different point of views on the same thing. And this is useful. This new point of view is useful because marked groups are isomorphic exactly when they are defined by morphisms with identical kernels. So this remark gives us the following lemma, that there is a bijection between isomorphism classes of marked groups and the normal subgroups of a free group. This is what helps us to define the space of marked groups. We equip the free group with the discrete topology, and then there is the product topology on the power set of the free group. And since we've seen that a marked group can be seen as a subset of the free group, this gives us the topology on the space of marked groups. All right, to clarify this, I'll give you a few examples. The first example is that of the sequence of finite cyclic groups, which converges to the infinite cyclic groups at infinity. I've drawn a picture. This picture actually contains labeled Cayley graphs, but I haven't drawn labels because we have only one generator for these groups, so each label is the same. The fact that this sequence converges exactly says that for every finite subgraph in the Cayley graph of Z, for every finite subgraph that you can extract, this subgraph is also the subgraph of the graph of finite cyclic groups. You cannot distinguish Z from finite cyclic groups using only finite parts of its labeled Cayley graph. This is exactly the convergence of this sequence. Now let me define the basic clopen sets. When working with the space of marked groups, we usually use the following basis for the topology. We fix two finite subsets of the free group, and we consider the set of marked groups in which the element of the first subset define relations, while the element of the second subset define non-relation. The set of groups that satisfy some imposed relation and do not satisfy another set of imposed non-relation. And these are clopen sets, and they form a basis for the topology of the space of marked groups. Few more examples. First, two easy examples of open or closed properties, like being abelian. This is a clopen property. The set of abelian group is defined by finitely many relations. You ask that each generator commutes with another generator, and you exactly get one of these basic clopen sets, which gives you the set of abelian groups. So that's a clopen property. Having an element of order 2, this is an open property. It's the union that I have written here. For all elements of the free group, you say that this element should be a non-identity element, and its square should be the identity element. And a group belongs to this union exactly when it has an element of order 2. These are very easy examples. Now, in fact, in some cases, determining whether property is open or closed can be very difficult. And the first example of this is having polynomial word growth. This is an open property because Gromov's theorem, which tells us that this is equivalent to being virtually nilpotent, directly implies that having polynomial word growth is an open property. But I don't think you can prove it without using Gromov's theorem. And so knowing that you have to use a very non-trivial theorem to prove that having polynomial growth is an open property. And another example is being of exponent p. This is always a closed property, but for some p's it is open, and for others it's not. And being able to say when it is open is very much related to the Burnside problem. And so and we don't know as of now for which p's is the set of exponent p group an open set. These are examples where it's very hard to know if the properties are open or not. All right, so now we have almost everything we need. We can start to talk about computably open and computably closed properties in the space of marked groups. There's one last problem we have to deal with, obviously, and that is we have to try and answer what is a computably open set. We have these basic open sets that define the topology of the space of marked groups, and we want to use them to define the computably open sets. So first, we should recall what are the open sets generated by a topological basis. When you know a basis for a topology, the open sets, a set is open if it is a union of basic open sets. Or you could say also that the set is open if for any point in this set there is a basic open set containing this point and contained in your open set. These are equivalent definitions of the open set generated by a basis. So now we'll do this with computability theory, and we'll copy and paste this, adding computable everywhere. So you say that a set is computably open if it is a computable union of basic open sets. Or you can say that it is computably open if there is an algorithm that, given as input a point in your set, outputs a basic open set which contains this point, and which testifies that this point is indeed inside of the set you consider. Either of these two definitions that I have written here are very natural definitions for the computably open sets. And it's hard, and we can ask, obviously, are these definitions equivalent? And in fact, in some settings, these definitions yield non-equivalent notions of computably open sets. Not much work has been done on settings where these give non-equivalent definition, because most of the times researchers are set in the context of recursive Polish spaces. And in this context, a theorem of Moskovakis tells us that the two notions of computably open sets that I told you about agree. And furthermore, an effective Borel hierarchy can be defined on recursive Polish spaces. Properties can be classified as computably open, computably closed. And you have hierarchy theorems, and there's a well-developed theory that you can apply. And in this setting, you can do exactly what we set out to do, and you have tools to do it. And I haven't defined recursive Polish spaces in this talk, and the reason is that the space of marked groups is not a recursive Polish space. This is very interesting because it means that the space of marked groups, even though it's defined in classical mathematics, right away there's some undecidability related to it. It's naturally a space which contains undecidability. So from a certain point of view, it's very interesting, but on the other hand, it's unfortunate for today because we wanted to have one good notion of computably open set, and we don't. We have these two notions, which I don't know whether or not they are equivalent on the space of marked groups. All right, so this theorem shouldn't tell you much since I haven't told you what is a recursive Polish space. So I have written here a more explicit theorem, which implies the previous one, but which hopefully we'll be able to understand. The theorem says there does not exist an algorithm that, given as input a basic clopen set, which contains a group with solvable word problem, outputs the word problem algorithm of this group. So if you recall that a choice function is a function which maps a non-empty subset of a set to a point in this subset, and that a possible way of expressing the axiom of choice is to say that every set has a choice function, you will understand how this theorem is related to a form of an effective axiom of choice. The theorem written here says that a certain computable choice function does not exist for the space of marked groups. You are given a non-empty basic open set, and you want to produce a point in this open set, and the theorem says there's no algorithmic way of doing this. And because recursive Polish spaces always have these type of, always satisfy this type of computable axiom of choice, this shows that the space of marked group is not a recursive Polish space. All right. So we are not in the favorable context where we have hierarchy theorems and where we know exactly what the computable open sets are, but this shouldn't prevent us from trying to classify group properties as computably open and computably closed. We just have to know that we have two notions and we have to use both of these. But when you're faced with a concrete group property, you can prove that it's computably open following this definition and computably open following that definition. It's not too bad that you don't have a general theorem that says that satisfying one is equivalent to satisfying the other. So I'll give you now a few examples of open and closed properties, and which are computably open and computably closed, starting by clopen properties, like being abelian being isomorphic to a given finite group, having cardinality at most n, or being nilpotent of derived length k. These are all clopen properties. Now some open properties like being nilpotent or satisfying Kazhdan's property T, being perfect or having torsion, being virtually cyclic, having polynomial growth, being polycyclic, or being a counterexample to one of Kaplansky's conjectures. And if you recall the recent breakthrough by Gardams, this boils down to finding a point in a computably open set in the space of marked groups in order to disprove one of Kaplansky's conjectures. Finally, a few computably closed properties, like being k-solvable, having finite exponent, being a limit group, and the set of limit groups is just the closure of the set of free groups in the space of marked groups. Being orderable, being delta hyperbolic, so this is not a group property, this is a marked group property, but in fact we're classifying marked group property, or having infinite conjugacy classes. Now, it turns out that most properties which are known to be open or closed in the space of marked group turn out to also be computably open or computably closed. And this is not ideal for what we set out to do in this talk, because if you recall the example about effective cardinality, the situation was interesting because introducing computability theory, we get a finer, we are able to make finer distinction. And this happens only when you find properties which are open but not computably open, or closed but not computably closed, just as we had that the set of finitely presented residually finite groups, while being countable, this set is not recursively enumerable, and it is for such examples that it is relevant to introduce computability theory. And for now, we don't have such an example in terms of classification in the space of marked groups. Fortunately, I have one and only one, but I do have one such example of a property which, while being closed, is not computably closed in one of the accepted in one of the two possible meanings of this. And it is the set of left groups. So we denote by F the set of marked finite groups. The set of left groups, which means locally embeddable in finite groups. The set of left groups is just the closure of the set of finite groups in the space of marked groups. And as a corollary of a theorem of Slobodskoy, which says that the universal theory of finite groups is undecidable, as a corollary to this theorem, I can prove that the set of non-left groups cannot be written as a computable union of basic open sets. So this means that in following one of the definitions we had of computably open, the set of non-left groups is not computably open while being open. And so the set of left groups is closed but not computably closed. Thanks to this, we have managed, this makes it so that the whole process of studying these open and closed properties from the point of view of computability, it does give us finer distinctions, and it will tell us more about group properties than just the classical classification, open and closed, without using computability. Let me remark that this corollary here this, for instance, explains in part why it is so hard to find a hyperbolic group which is not residually finite. This is a well-known conjecture that such groups exist, and no one has been able to find one. And the corollary written here exactly says that finding a non-left group is harder than finding a group in other kinds of open properties. Finding a point in a computably open set is easier than finding a point in a non-computably open set. And this says that finding non-left groups, which in case of hyperbolic group is equivalent to finding non-residually finite hyperbolic group, is harder than it would be if it was a computably open set. All right. To end this talk, I wanted to give 4 more examples of properties which I conjecture are open but not computably open, or closed but not computably closed. And these examples are as follow. The closure of the set of hyperbolic groups is closed but not computably closed. This is a conjecture. Closure of the set of finite nilpotent groups, closed but not computably closed. On the other hand, the set of finitely presented simple groups is probably open and not computably open, and so should be the set of isolated groups. And isolated groups are groups that define open points in the space of marked groups. Let me just remark that the conjecture about finitely presented simple groups is very much related to the conjecture which says that this set of finitely presented simple groups is probably not recursively enumerable. And this is also related to the Bohm-Higman conjecture, and it attracts a lot of our attention these days, but we still don't know whether or not this is the case. All right, thank you for your attention. That's all I wanted to tell you about today.